Hey there, Dr. D, and here's my explanation of the X-ray circuit. So let's go ahead and start out with the incoming line current, which is the power that's supplied from power companies over to the user. So that's going to be 220 volts at 60 hertz to the building. As soon as that energy hits the X-ray circuit, that's actually going to go cut down to 110 volts at 60 hertz. Now let's go ahead and get our settings out of the way. 120 kVp at 25 milliamperage for 3 seconds. So let's go ahead and flip that switch, or that main switch at the control panel. As soon as that happens, 3 lines are going to go ahead and fire up simultaneously with electricity, 2 going to this auto transformer and 1 going to the variable resistor. So let's just go ahead and run with the variable resistor side, or the milliamperage side. So we go ahead and input our 25 milliamperage, which is read by the filament ammeter, and once it's read by the filament ammeter, it relays that information to the variable resistor, which goes ahead and selects that milliamperage based on whatever notch it wants to be pointed at. Continues up this and goes all the way up to this line. Now we can see that this line is not physically connected with the auto transformer, and that's for a main reason. If it was physically connected, the circuit would confuse whether or not it's getting kilovoltage or milliamperage. So it's separated for that specific reason. In order to continue and get that current across this little gap right here, we're going to do that through induction. And induction is a process where whenever there's a charged object near a neutrally charged or a conductor, that charge will actually jump that gap, and it will induce that current over to that conductor. So before we dive any deeper, there's a couple points where this happens, and I'll explain that when it comes. So we have point 1, 2, 3, 4, 5, and then there's a 6th one that will be in the X-ray too, but we will cover that when we get there. So continuing on from there, so we talked about the 110 volts that is supplied to the whole circuit, so that's continuing down right here, and we can see in this primary coil right here that there are more coils than there are on the secondary coil, so this therefore would be a step down transformer. So jumping down and stepping down that voltage, we go from 110 volts to 5 to 15 volts, because anything higher than 5 to 15 volts, you could short out the filament, it could burn it out or anything. So 5 to 15 volts will be perfect just for the X-ray tube. So this will continue that connection all the way up into that X-ray tube. Now, as far as the kilovoltage side, so we're going to have our 120 kilovolts that is read by the kilovolt meter. That will relay that information over here to the auto transformer. And this notch will go ahead and do the same thing like that variable resistor action, where it'll just kind of turn its notch to whatever respective setting it needs to be. Now this also happens at another time, which would be the last section, the timer. So we have our 3 seconds right there. Input that into the control panel. Timer will read that setting of 3 seconds, and then it'll relay that information to the exposure switch, which makes sure that whatever we're radiographing will only be exposed for 3 seconds. Now, let's go ahead and continue. So we have that 110 volts we're talking about, right? So we can see in this primary coil right here, we have less coils compared to the secondary coils. So this would make this a step up transformer. Carrying on, we have that 110 volts would now jump up to 10,000 volts. Now we can see there's this another meter right here, and this meter has 2 jobs. It'll calculate the MAS, which is the milliamperage times the time, or the seconds. So it'll carry that out, and the second function is to make sure that when we step up in voltage, that it is truly going to be 10,000 volts. Now, so let's say there's a scenario where it's 6,000 volts instead of that 10,000 desired point. So if it's 6,000 volts, it won't even make it past the primary circuit side. It'll just stay here until it reaches that necessary charge for 10,000. Now, let's say we're overcharging it and it hits around 13,000 volts. In that case, the excess would be stored right here. This thing right here, this triangle shape right here, that's going to be the ground. It would just store that overcharge over in here. Now, let's go and say that the meter has already verified the correct MAS, and it made sure that it's going to be at that 10,000 volts. So everything went right, we're at 10,000 volts. Now we're going to go ahead and continue through. We're going to go have the capacitors. So those 10,000 volts, every time it's surged, it's going to go ahead and be stored in the capacitor. So the capacitor will it's just necessary for holding that much charge, because 10,000 volts is going to be a lot of electricity. After being stored in capacitors, we have the falling load generators, which kind of releases these 10,000 volts in like drops, little drops. 10,000 here, 10,000 there, 10,000 here, making sure that it's not going to be a lot of 10,000, coming all at the same time, which could short out the circuit. As soon as that happens, we're going to go ahead and move from the falling load generator over to the rectifiers. So As far as the rectifiers, there are two main types, or two main pathways. So there's this first pathway where it goes up and over here, follows through, goes down, up, makes this kind of 4 action, and then goes back to that coil. So we can see these things right here are called diodes, and one of the main functions of the diodes is just to make sure that the electrical current only maintains one direction. So we can see whatever line this little line right here points in which way it's going to pass through. So it has to continue like this because we don't want anything jumbling up, crossing paths or anything like that. So the secondary one is going to be this one. So it goes from the bottom up, make that little turn, up here, and to the coil. And this is one of the pathways where it happens 4 times. Yep, 4 times right there. So the rectifiers is making sure that the diodes are making sure that everything's flowing in one direction, and then it's releasing, rectifiers will change it from a alternating current to a pulsating direct current. And the pulsating direct current is the most efficient for X-ray. So while this is all happening at, it seems like it's all like one by one, but it must be noted that everything is happening at 1 consecutive second because electricity moves that fast. So everything on the kilovolt side is happening, everything on the variable resistor or the milliamperage side is happening at the same time. The rectifiers and the meter making sure it's all 10,000 volts. This is all happening at the same time. So we talked about as far as the filament side, this is going to supply on the negative side or the cathode side. And then as far as this top side, the step-up transformer, this is going to go ahead and connect to the positive side, the anode side. So let's go ahead and continue. So on the positive side, the stator electromagnets will get this, they're powerful electromagnets which will get this charge. And we have the rotating portion or the rotors, and these are just in the middle of these stator electromagnets. Now we learned in previous chapters that when there is a conductor, such as the rotating portion within these magnets, within the magnet's magnetic field, it will produce it will produce movement. So this rotating portion or this rotor will kind of be moving back and forth, which will tilt this whole anode assembly. So we have the molybdenum neck and base right here, these 2 parts right here, which will have a melting point of 3,170 Celsius. So this is going to kind of move it, keep tilting it. That whole movement action is occurring, and this is ensured through the bearings. The bearings kind of make sure it stays in place, it stays, lubricated, it's moving very well, and so it'll rotate that. Okay, so that's just for the positive side. So we just established that this is rotating and tilting back. Now let's go ahead and talk about the filament side. So electricity surges through here and follows through this cathode assembly. The cathode is made up of 3 parts. We have the filament, which is this small kind of B-shaped thing right here. This focusing cup, which is this kind of like half square right here. And then these lines right here are going to be the associated wiring. So let's go ahead and continue with this. Travels down the cathode assembly. We see at this filament right here. And then we also, on this little half square right here, this is actually the focusing cup. So this focusing cup is lined with electrons right here, negatively charged electrons. So then it'll repel any other charges because of repulsion attraction theory, or law of repulsion attraction. So it's lined with those electrons. It'll make sure that no electrons try to go out and above. It'll just repel them down forwards. So this cathode assembly will create a thermionic cloud or shoot out electrons, other known as the electron beam, that goes in and shoots out at this tungsten heel or this tungsten anode. Now tungsten, we want to use tungsten in the X-ray circuit for 3 main reasons. Its high atomic number, its high melting point of 3,370 Celsius, and its high heat conducting ability. So keeping that in mind, so the thermionic cloud or that electron beam will kind of shoot out from the cathode. It'll bounce off this heel, which is angled at 12 degrees, and that will shoot downwards, and that will create our X-ray beam or our X-ray photons. Now, there are a couple inefficiencies with this. When it hits the the heel, if the angulation is off or the target area is off by any chance, that these electrons can actually bounce out. And when it bounces out, it'll kind of make a deposit. It'll start to build up on the envelope. Now, let's just go ahead and cover what envelope is. So the envelope is the casing or the kind of the shielding of the X-ray tube. It is meant to make sure that it stays in a vacuum environment, as well as it helps with cooling. So it'll actually, when it hits off this right here and it makes those misfires, I guess, miscalculations, it'll store up on the outside of the envelope, which will create an inefficiency. And that specific failure right there is going to be called tube arcing. Another one is where this filament right here, whenever it is exposed, it starts to withstand heat. Now, over time, if it goes to those repeated like exposures to heat, the filament, when 10% of the filament has dissipated, it can actually be subject to breaking, and that would just be called filament breakage. So that's the other failure that we have to worry about. So then again, let's just go ahead and run through this one more time. So the stators are right here, very powerful magnets. Go ahead to different poles and makes those magnetic fields. Now we have the rotors, which are a conductor, and we learned in previous chapters when a conductor is within an electromagnetic field, it'll start to move. So this is kind of moving it along with the armature, and it's connected to the whole anode assembly, and it's just kind of tilting it back. This is happening really quick. We want this to happen really quick so then it can dissipate heat really well. Because when we're dealing with something like the X-ray circuit, high voltage applications, we really want to make sure it's moving quick so it can do proper heat dissipation. So that's moving. The electricity is supplied on the negative side or the cathode side, goes down the cathode assembly, is shot out, made from it's a thermionic cloud that is shot out. The focusing cup makes sure it keeps it's not gonna get every electron, but most of the electrons are kind of like gathered together, shoots it out, bounces off that ideal angle of 12 degrees of that tungsten anode, shoots down into whatever is being radiographed as X-ray photons. So that's my little personal take on all of this. Thanks, Dr. D.